So now we are about to start this new chapter which is called quantum physics. And in quantum physics, one of the first ideas that we'll talk about, and this is our entire motivation actually for studying this chapter, is that what is the nature of light? Is it a particle or is it a wave? And this is a very interesting conversation that has gone on for a couple of centuries now. And all of the scientists have had their different inputs on it. So first of all, let's see how do we have this evidence that light is indeed a wave. So you might remember from all the waves and the superpositions that we've studied in AS that we actually do have a lot of evidence that light actually behaves like a wave. So for example, we know that waves undergo reflection, they undergo refraction, they undergo superposition. These are all things that we expect of waves. And then obviously the superposition also leads to interference. We also see waves showing us diffraction. This is not something which is typical of particles. So diffraction is also something which is explained using wave theory. And also another phenomena that we studied called polarization is also something that we expect of waves and not of particles. So 1, 2, 3, 4, and 5. These are some of the wave phenomena that we associated with light. And there as well, I just gave you a slight idea of this, that if any particle that we come across, if it shows any of these 5 properties, so this gives us enough reason to say that yes, this is something which behaves like a wave, so it should be classified as a wave. This is actually how we talk about something being a wave or a particle, depending on what are the phenomena that they undergo. But then in modern physics, what we call it, so towards like the 19th century, we came across a couple of experiments, a couple of observations, you may call them, which were some things which were not, or rather we should say that it could not be explained by the traditional wave theory and the wave concepts that we were talking about. So that gave us some reason to doubt all that we had been doing so far, and then this gave us a reason to classify light as a particle. So in one of these, and this is one of the primary ones, this is something we are going to be talking about a lot in this chapter. That is called the photoelectric effect. This is one of the main reasons, and this one we'll be talking about in a lot of detail as to how the wave theory fails to explain this idea. In a while, we'll also be talking about the emission and absorption line spectrum. So how the line spectra also gives rise to the idea that particles, light exists as particles, and how it gives rise to what we call these discrete energy levels. And something else which is not really part of the syllabus, but you can look into it for your own interest as well. That is also something which gives proof that light is indeed a particle, is something called the Compton effect. It's sort of similar to the photoelectric effect, but there's a difference in the energy levels. So the outcomes are slightly different, but the end results are the same, that all of these show that lights are particles and all of these show that lights are waves. So at this point, it's also worth talking about how scientists do experiments and how do theories work. So up till this point, what was happening, so up till the 19th century, I mean, or towards the end of the 19th century, we should say, to be more accurate, is that wave theory was serving us very well with regards to the things we saw and the things we wanted to explain. But when these things came about, the wave theory failed in explaining them, which is why we had to understand and we had to develop a new theory, and then we had to see whether that theory actually helped us explain how light works, right? And this theory of lights as particles actually worked pretty well in explaining all of these effects. And soon we'll see this in a lot more detail. So just a very small intro of this theory of particles as, or the theory of light as particles, is that we say, or actually this is what Albert Einstein said, and this is actually why he was awarded the 1921, I think, the 1921 Nobel Prize. So what he said is this, that all the electromagnetic radiation, and not just light, is made of photons. So a photon is just a packet of energy of electromagnetic radiation. And this is a sort of a peculiar particle as compared to all the ones we've studied, because this particle has no mass, right? So this is a packet of energy of EM radiation. What we also say here is that this energy is quantized. So that means that you can have 1 photon or 2 photons, but you can't have 1.5 photon, right? So the energy is quantized. It is, for example, you can say this is in discrete amounts. It's not continuous. So you can have 1 or 2, but you can't have 1.5 or 1.3. So this is another important concept. So it's in steps. You might also remember it like this. So this indication to quantization is what this definition makes when it says a packet of energy, right? So it's not like a continuous stream, it's like in packets, it's in discrete amounts. So as I also said, it's a massless particle, doesn't have any mass associated with it, and the energy of a photon, because it is a packet of energy, the energy of a photon is proportional to its frequency. This is an important thing. Now, as with all proportional relationships, how we work with this is we multiply by an appropriate constant of proportionality. So this equation then becomes E equals hf as the energy of a photon. Now this is a very important relationship. I'll also talk about what h is here. So E is the energy of a single photon here. So it is the energy. So energy of 1 photon. H is something called Planck's constant, named after the scientist Max Planck. The value of this is 6.63 into 10 to the negative 34. And it's also pretty easy to see that its units would be joules second, because frequency is the frequency of electromagnetic radiation, which is in hertz, which is basically the same thing as per second. So the per second and the second would cancel out, leaving us with joules as the unit for energy. Since all electromagnetic radiation travels at the speed of light, and we know that we can call the speed of light c, the product of the frequency of radiation times the wavelength of radiation, that also allows us to write the energy of a photon as h times the frequency, which we can write as c over lambda. So just like how we said that the energy is proportional to frequency, it's the same thing as saying that the energy is inversely proportional to the wavelength of radiation. So if we do a really small primer, you can call it, on electromagnetic radiation, so we can draw this spectrum here. This is a thing that you might already remember. And let's say that if we start from the longest wavelength radiation, so that's radio waves, then we have microwaves, then we have infrared, and then we have visible light. And in visible light in itself, we have a spectrum of colors. So if you're starting with the greatest wavelength on the left, let's do the same for the visible light colors as well. So you have red, orange, yellow, green, blue, indigo, and violet. And similarly, if we go further with the rest of the EM spectrum, so after visible light we have the higher frequency orders. So you have ultraviolet, then you have X-rays, and then at last you have the gamma rays. So previously in AS we've talked about this in a lot of detail. we've said that in one particular order, let's say if I'm talking about the line like this, you know that the frequency is increasing in this order, and you can also say that the wavelength is increasing in the opposite order, because all of these have the same speed of light. So if the frequency of something is increasing, that also implies that this wavelength is decreasing. So right now, if I say that this is the order of increasing frequency towards gamma rays, and here I can say that the wavelength, so the wavelength is decreasing, the wavelength is increasing in the opposite order. That's the same thing. And now that we know that the frequency also determines the energy, I can say that in this way, as the frequency is increasing, I can now also go ahead and say that basically the energy is also increasing. And similarly, in the opposite way, as you can see that the wavelength is decreasing, the wavelength is increasing, that means the energy would be decreasing. So let's actually try to find this out, even though right now we don't have much of an idea of what a photon is or how it works. That is something that we'll be covering in the lectures to follow. Let's say that we find the wavelength. So let's find the photon energy. For red light, which has, so red light, you may remember, has a range of wavelengths. Let's say right now this is the one of the longer wavelengths. So let's say this is 700 nanometers. Right, we need to find the photon energy corresponding to this wavelength. So if we go ahead and write down the formula, E was equal to HF. In terms of wavelength, we can write this as hc over lambda. So H is Planck constant, 6.63 into 10 to the negative 34. C is the speed of light, 3.0 into 10 to the 8. And lambda here is 700 nano, so 700 into 10 to the negative 9. So when we calculate this value turns out to be 2.84 into 10 to the negative 19 joules, correct to 3SF. Now, with all the photon energies that we'll be finding, we'll see this 10 to the negative something, which is a really small number. So 10 to the negative 19 or 18 or 17 is what we'll be usually encountering. Obviously, it is redundant to write down this 10 to the negative something, a very small number basically here, when we know it's always going to be this small. So for this purpose, we introduce another alternative unit of energy in the context of quantum physics, that is called the electron volt. And it's written as EV, and it's defined like this. So this is the energy gained by an electron when it is accelerated from rest through vacuum through a potential difference of 1 volt. And now this is also really easy to understand, just requires a bit of the AS physics that we studied. Remember how we talked about the potential difference there as being equal to the work done per unit charge. We can also rearrange this to call it the work is the product of the voltage or the potential difference times the charge. So here if we have one electron, so we can see here that the work would be 1 volt, that is the potential difference applied, and the charge of an electron would be 1.6 into 10 to the negative 19 coulombs. So then how we define 1 electron volt, this is the definition of the electron volt as we just saw. That is basically 1.6 into 10 to the negative 19. Volt coulomb is basically the unit for joules. So this is how 1 electron volt is defined. This is also an important result to remember. The conversion of this is often tested in the paper. Another sort of a modification of this result is that if we want to write this instead of in electron volts, a closely linked result could be if I want to talk about a mega electron volt, which is just basically 1 electron volt times 10 to the 6. So it's 10 to the 6 electron volts. So this turns out to be 1.6 into 10 to the negative 13 joules. So let's say I want to write the energy above that we just found out, 2.4 into 10 to the negative 19. Now I need to give that energy in electron volts. So write the energy in electron volts. So it's very, very simple. Just need to use the unitary method once again. So we want to write, let's make a small table of sorts. So this is electron volts and this is joules. So we know that 1 electron volt is 1.6 into 10 to the negative 19 joules, and we need to find 2.84 into 10 to the negative 19 joules. How many electron volts is that? So from here on, we just need to cross multiply. You can obviously see that this amount in electron volt would be 2.84 into 10 to the negative 19 divided by 1.6 into 10 to the negative 19. You can also just remember this always in this way, that whenever you need to convert to electron joules, you just divide by the charge of 1 electron. So this turns out to be 1.775, or we can say 1.78 electron volt, correct to 3SF.